All right, for the sake of time, we're going to get going on this project. So this is the Missouri River Bridge project. My name is Mara. This is Jonas, Paige, and Gabe. So we worked pretty closely with the Lincoln Highway Group to determine a location for an additional crossing over the Missouri River. As they mentioned, this route and the bridge would divert traffic from the Bismarck-Mandan area, as well as creating a more direct route to I-94 and incorporating the city of Lincoln into that route as well. So our project focuses primarily on the bridge itself and the necessary steps that we have to go through to add this crossing to the area. So that is the structural, environmental, and economic aspects of getting a project of this scope going. So this new bridge would become the southernmost crossing in Bismarck. The current southernmost crossing south of the Expressway Bridge in Bismarck is in Mobridge, South Dakota. This is a closer look at the proposed project location. So as they talked about in the highway project, the bridge would connect on the east side of the river from 48th Avenue, cross over, and then tie into 1806 on the west side of the river. We looked at a lot of the crossings that already exist for design inspiration for our crossing. And so we're going to get started with permitting, which was the first step, and Paige is going to talk about that.
So for this project, a lot of time and research went into determine which permits and agencies needed to be contacted in order for us to build this bridge. Federal law prohibits the construction of a bridge over a navigable waterway unless first contacting the United States Coast Guard and getting it approved. So the key step in the permitting process would be to obtain that U.S. Coast Guard bridge permit. This permit looks at the bridge design and makes sure that it meets both building and safety regulations along with environmental and land use regulations. So the required documents for this permit would include looking into NEPA, Section 401 of the Clean Water Act, which deals with the drainage of water into a navigable waterway, which the Missouri River is considered. A Section 404, which deals with the dredged material from the riverbed. Floodplains and floodplain permits. And then the Endangered Species Act, along with other permits that would be obtained later on. It should be noted that the proposed bridge is going to be constructed in the floodplain. This was verified by FEMA floodplain maps, but it should be noted that there should be no rise in the headwater, which will comply both with FEMA and NDDOT design regulations. So as I stated, with the Endangered Species Act, with the biological assessment, NEPA and the Endangered Species Act will interact to make sure that any action taken on the proposed location will not jeopardize the continued existence of a threatened and endangered species. So what the biological assessment does is it looks at all the species in the project location and gives them kind of like an impact rating. So as you can see, some animals will have been not affected at all by this project, while others may be affected, but there'll be no adverse effects on any of these animals. Specifically, we looked into the piping plover. The piping plover prefers sandbars and large shorelines to live on. And so though the Missouri River is considered a critical habitat for the piping plover, the proposed project location is not suitable for the plover, so we do not intend to affect it anymore. And then for all of these animals, it should be noted that we're not affecting them any more than regular river recreation already does.
Some additional permits that we looked into were we obtained a wetland map from U.S. Fish and Wildlife Service to see if our project would be crossing over any wetlands. So as you can see here, this is 48th Avenue, and then we travel across the bridge here, and it doesn't cross through any existing wetlands. So that was actually taken into consideration when choosing the project location, just to ensure that we would not have to obtain that permit. We also looked into the North Dakota Sovereign Land Permit. This permit is necessary if the project lies within high watermarks of a navigable stream. So like Paige mentioned, the Missouri River is a navigable stream. And so this permit would be necessary, and obtaining the permit would give authorization to construct in this area. We also did a soil analysis to see what types of soil we have on both sides of the river. So as Dalton mentioned in the last project, we utilized a free online resource called Web Soil Survey, where you can put in your project location and it'll tell you the surveys that have been taken of the soil in that area. So as he mentions, these orange lines represent the different types of soil. So for example, here E425B, which is a sandy loam, which is specified in, they give you an index of all the different soils that are in your project location. So we found that on both sides of the river, there's varieties of loams, and these would be sufficient for a bridge foundation. We didn't look into the riverbed soil as that was kind of beyond the scope of the project, and those resources are harder to obtain. But we did obtain the BNSF Railway Bridge, which is 5 miles upstream. We got their boring logs to look more specifically at the different types of soil at deeper depths, just to ensure that it would be stable enough for a bridge. And so since that location is only 5 miles upstream, we assumed that the soils would be of similar composition.
So while we were designing the structural elements for this bridge, we decided to base our design off the Grant Marsh Bridge, which is existing in Bismarck. The major difference between our bridge and the Grant Marsh Bridge is length. Our bridge is nearly 3 times the length of the Grant Marsh Bridge, which is only 1,125 feet long. And our bridge is 3,500 feet long, roughly. We have pier-to-pier spans of 220 feet, which gives us 15 piers overall for our bridge. And then while doing structural design analysis, we used codes and specifications from the North Dakota Department of Transportation, the American Society of Civil Engineers, specifically documents 716 and 722, and then AASHTO, ACI, and AISC. And all structural elements for this bridge were designed using the load and resistance factor design method. So this is a cross section of our bridge, just a small little chunk of it. And it shows pretty much all the structural elements designed for our bridge, except for connections, which are not in this model. As you can see, there are reinforced concrete piers, columns, and beams. And then there's also a 8-inch reinforced concrete deck. In addition to that, we have precast concrete barriers and medians. These did not require any design work on our part because they are specified design by the North Dakota Department of Transportation. And then we designed 7 steel plate girders to run across the bridge to span those 220 foot lengths. Additionally, between these girders, we have steel bracing, which are W8x10 steel members. And that just helps counteract torsional forces and provide lateral stability for our bridge. The biggest challenge faced while doing the structural design and analysis for this bridge was finding girders to run 220 feet. For cost purposes, we wanted to keep piers limited because every pier adds an additional almost like $500,000 to the project, not including foundations. And so we wanted to limit that as much as possible. So our 2 options for spanning 220 feet were pre-stressed concrete girders and steel plate girders. At first, we were looking into pre-stressed concrete and just found that the maintenance and overall construction of that is far more expensive than the steel plate girders. So we ultimately went with steel plate girder design. Here's a little graphic on the slide that shows what our steel plate girders look like. And just to give you a little perspective, they are a little over 6 feet tall. These are designed specifically for this project because there are no existing steel sections that satisfy the requirements we need. And they were designed based on span and loading, with expansion joints between each girder for extreme temperatures, expanding and contracting of steel. Something I found interesting while we were designing these steel plate girders is that we designed them to withstand shear, moment, and deflection. And in the middle of the girder between the piers, it deflects less than ½ inch. So for steel reinforcing and steel bolt connections, we specified for all the major connections in our project. And the steel reinforcing is for all the reinforced concrete members, obviously. As you can see in the little diagram, we do have some welds just to keep the steel braces in between the girders. And those are all 1/4-inch welds all around.
So as addressed in the permitting section, the Clean Water Act requires specific regulations when it comes to the drainage of water into a navigable waterway. So since we can't just take the rain from the bridge deck and have it flow into the river, a specific drainage system was designed. And in particular, we went with a closed deck drainage system, which can be seen in both these images. How that works is the water flows off the deck into the gutter all the way into the inlet and then flows down the structure into the ground. And so to begin this, so after Gabe and we all decided to, on the bridge design, we started the drainage system design as well. We started by looking at the impervious area of the deck to determine how much water was going to flow to each of these inlets. We then looked at an IDF curve for Bismarck to determine the time of concentration, which is the time it takes for the drop of water to flow from the farthest point of your watershed to your inlet. After we had those values along with others, we started calculations and we used things from the NDDOT design manual and other standards to determine these calculations. And these calculations showed that we needed 2 drains. This meant that 1 full width drain would be placed on each end of the bridge.
All right, so at this point, we decided to do a life cycle cost analysis. We wanted our bridge to overall last 100+ years. If it lasted more than that, that'd be great, but obviously we planned for it to last about 100 years. That would include the piers, the foundation, and most importantly, the pavement. So when looking at the pavement, we need to consider things like yearly maintenance, such as the crack sealing, joint sealing, cleaning, and the resealing. So for our life cycle cost analysis, we looked at 2 different pavement thicknesses of 8 inches and 4 inches with determining cost efficiency and which would last longer. So for the 4-inch pavement, it would require double the maintenance to keep it sustained. It would require a full deck replacement after a certain time period, probably right around like the 50-year mark, half the project life. The total project cost would be around $26 million with labor and construction included. The 8-inch pavement would require about half the yearly maintenance. It would not need a deck replacement with keeping up with that maintenance. It would cost right around $25 million. So overall, we decided to go with the 8-inch thick pavement. After completing this life cycle cost analysis, we did determine that per NDDOT standards, 8-inch thick Portland cement pavement is the minimum required for a bridge over water. And so we went with that because the yearly maintenance will be half, it'll last longer, it won't require a deck replacement, it'll last the entire project life. And then below, a little example of how we got that yearly maintenance cost associated. And then, so we had to come up with a basic construction phasing plan. So the phase 1 would be site inspection and planning, mobilization of equipment. This would include determining where our site is, keeping everything safe and making sure the habitat is not going to be ruined, getting all the equipment to the site. Phase 2 would be setting a silt screen and cofferdams. The silt screen would be put downriver of where our bridge is going to be, collecting debris or anything that might fall into the river. And the cofferdams would be built around where we're going to put our piers to keep them dry and make sure the concrete is not getting wet during the setting of the piers. Phase 3 would be setting the foundation for the pillars. Phase 4 is adding piers and bridge supports. Phase 5 would be adding the superstructure, which is everything on top of the piers. And then phase 6 would be quality and safety inspections. And then after that, we'd make sure everything returns to its original habitat.
So that's the process that we took to design a new crossing over the Missouri River, inspired by the crossings that already exist in the Bismarck area. So we've thoroughly looked into the economic, environmental, and structural aspects of the project in order to produce a sufficient and sustainable bridge. Thank you for your time and attention. Yeah, so we actually, at the beginning of the semester, we met with all 3 civil projects are kind of tied together. And so that was more so in, you'll see in the next project and then also in the previous project, more of that traffic analysis, as ours is just the crossing that would tie into that roadway that they're creating.
the cost that you have, that you presented, is it only for the construction, or does it take care of also the maintenance throughout the whole 100 years?
Yeah, it does actually. It includes the maintenance of the 100 years. It includes the labor, the construction costs, and all the materials.
And how do you take inflation into consideration throughout the whole?
Just, well, obviously, for example, for COVID, we had a tough time, tough to get the materials. So as you go, we definitely want to start this project right away. Make sure we get materials ordered right away, so we don't have to come up with reoccurring costs down the road or something that changes down the road.
I had a similar question, Rodrigo. Going back a couple slides, do you guys use the time value of money at all to figure out that $250,000 replacement for the deck at 4 inches, and then your annual maintenance costs? I don't think those would be consistent over that 50 years or 100 years. Did you actually put those into that 25 million X dollars for your calculations?
I didn't use the time value like you said. I just kind of used like a present value basically. So.
So as far, you said, the span was 220 feet for the bridge. And then the girders deflected less than half an inch. Did you consider using a smaller girder and accepting a larger deflection?
Yes, we did consider that. The load case that actually controlled was flexural strength. So actually the required flexural strength was met just barely by this design, whereas the deflection was exceeded.